Kristan Jensen that will tell us about normal of the Hartle-Hawking state in pure dS3 gravity.
Yeah, so thank you very much for the invitation. It's lovely to be back. I'm going to be discussing rather informally some work in progress with Jordan Cutler. We're still dotting a number of I's here, so hopefully this is going to be some stimulating, interesting discussion. Please ask lots of questions and so on and as needed. So this is all about de Sitter quantum gravity, and the example that we'll compute in some detail is that of de Sitter in 3 dimensions. So I just have in the back of my mind pure gravity, nothing else in 3 dimensions. That's boundary terms. Although I'll try to say a few things at the beginning to set the stage that will be true for de Sitter in any dimension. And the attitude that I'm going to take in this talk is not to worry about all manner of deep and important questions that come to the head whenever we utter the words de Sitter or accelerating universes, like their existence and whether or not they're metastable, eternal inflation, et cetera, et cetera. I'm not going to worry about any of these things. I want to try to make sense of effective field theory, de Sitter vacua, on its own terms, taking the gravitational path integral seriously, as we have learned to do in an ADS setting these last several years. So in this context, our basic solution, we'll start with to orient the discussion, is just that of global de Sitter space, which has a line element, just minus dt squared, r squared t, d omega squared, in the standard square Penrose diagram, where here, this is past infinity, future infinity, attained as I take t to minus and plus infinity. And then there's various patches that people commonly talk about in de Sitter. There's an inflating patch up here. There are many static patches in which there's a time-like killing vector field in the patch. One of them is given by this triangle right here. And there's a complementary patch over here. And there's a bifurcate cosmological horizon separating the two. And at least in these coordinates, I can write, in other coordinates a line element on the static patch that's minus 1 minus r squared, some time d tau squared, r squared, d phi squared, dr squared, 1 minus r squared. And then this cosmological horizon is sitting here at r equals 1. And an elementary question of de Sitter quantum gravity that has yet to be resolved is, what on earth does this horizon mean? Something people still argue about. So we can associate an entropy, area by 4g Newton, with it. And don't call it an entropy in quotation marks, I don't know what it's counting. In this case, it would be pi by 2g Newton, since I'm effectively in units where the radius of the de Sitter is 1, then plus loop corrections, and so on. But what is it? Is this counting some number of states that I would associate with the static patch? Is it counting some entanglement between the static patch and the complement, and so on? Does it correspond to a dimensionality of Hilbert space of states in the static patch? Does it correspond to, number of counting initial conditions that I can create on stride minus that'll make it all the way to stride plus without crunching? What is it? Is it even important? I'm emphasizing all these questions. Another way of saying it is to say that, unlike in the context of ADS quantum gravity, where we have a central dogma that we've been following very productively for a number of years, that black hole entropy is and it counts microscopic states. Here, it's less clear. maybe there's such a central dogma that tells us to focus on the cosmological horizon, maybe it's not. Some difficulties that do appear if we try to take this thing seriously as a measure of state counting are the following. So one is, if I ask about this horizon entropy in terms of Euclidean gravity path integral, then Gibbons and Hawking famously argued that this E to the S should be understood as the sphere partition function, d dimensions, Euclidean gravity. The basic idea there is that in the static patch, we can think of the vacuum that state in the patch as being prepared by a Euclidean cap that we glue into the time symmetric surface at t equals 0. It's a hemisphere, and follows kind of the same arguments that would lead you to writing a Euclidean path integral for the black hole entropy. You end up arriving at this statement that E to the entropy of the horizon should be the sphere partition function. And that's problematic because if I go beyond tree-level physics and I ask about the sphere partition function at one loop, well, this has a phase. It goes in d dimensions like I to the d plus 2. This is originally noted by Polchinski. So that's, and why is that an issue? Well, at least in 4 dimensions, this is negative. So in what sense can I say then that this is counting states? It's unclear.
Remember which year this was?
What's that?
This Polchinski paper?
I don't remember. I'll find it and I'll send it to you. I don't remember. It's from the 80s. What's it?
Late 80s.
Thank you.
Yeah, it's in the 80s.
So can this space be eliminated for a change of contour?
No. Okay. There was a lot of argument at the time suggesting that this is the case. I can give you the one-line argument for where this phase comes from, and it also makes it clear it's independent of the contour. So of course where this phase is coming from is because the conformal mode is wrong sign in Euclidean gravity. So the natural thing to do then is to rotate it so that it becomes right sign. But the problem, and that incurs no cost, no phase, because you've rotated the whole mode. However, what happens is that even after rotating the whole mode, on the sphere, there are certain modes of the rotated conformal mode that are wrong sign. So you have to rotate those back. There's a finite number of such modes. In fact, there's d plus 2 of them. That's where this comes from.
Is it one reason I had a paper try to address this?
Yeah, that's right. So, with the best paper title of 2024, in my opinion. So
What?
Well, it's in the real observer solves the imaginary problem.
Oh, yeah.
It's a fantastic paper title. So, the idea of that paper, since we're talking about it for a moment, is to, with the problem that was recently considered by Jeff and Edward and Longo and Ben Kates. I've only met him once, I don't remember how to pronounce his name. You guys would know, so let me not butcher it. When they were constructing an algebra of observables in the static patch of the center, so where you have an observer kind of at the center of the static patch, there's an observer in the complementary static patch, and now you can define some interesting algebra of possible local observables associated with it. If I'm trying to prepare the state, the vacuum state with the observer in it, in the static patch, I can do that with a hemisphere that has an extra particle in it along a great circle. And then the analog of this would be a sphere, but then where this observer traverses a great circle of the sphere. And if I consider the coupled system of gravity plus this observer wrapping that great circle, well, now there's extra wrong sign modes coming from the transverse scalars of this observer world line. And that leads to enough factors of I to kill this and give you a real answer.
You have to put in the observer as an additional system.
That's right, exactly.
That seems totally unphysical to me.
I was asked to face a connection with Juan's paper.
Sorry, it's not meant as a criticism.
Yeah.
I'm just trying to-
Yeah, okay, so that's the result, and from the point of view of counting states, in pure gravity, without adding anything, this is still very confusing. There's also the question of, well, which static patch are we talking about? There's many static patches, there's not just one. There's also the annoying feature that the existence of the static patch is sensitive, like the details of the static patch are sensitive to the initial conditions. So if I send in a rock from stride minus and send it forward, it will alter the causal structure of de Sitter, it will lengthen the Penrose diagram, and it will change this considerably. The last thing that sort of bugs me about this, or maybe I can pose it as a question, in my HEP-QIS part of parts, I'm a quantum field theory and ADS CFT person, and so from that point of view, I want to discuss bulk physics by means of boundary, which in this context is up here and down here. And if I'm talking about black hole entropy, well, I can do that. Black hole entropy is CFT entropy. Well, what is this from the point of view of physics at infinity? Another way of asking is, can I reconstruct this horizon entropy from physics at infinity? Say from stride plus. So those are all sort of things to set the stage here. Now, I'm going to radically switch from all of this that we've just talked about to a seemingly unrelated problem. And then we'll see by the end of the talk that the two are intimately connected, which is a completely different question of whether or not there's a natural state of the universe in de Sitter quantum gravity. And, well, I'm not going to say what a natural state is or isn't in this context. Let me just recall that there's a lovely proposal due to Hartle-Hawking for such a state. It's invariant under the de Sitter isometries, just a no boundary proposal. Which, at least if we're in global DS, how does that read here? The way that it reads is that rather than the universe being generated from a Big Bang or from a whole asymptotic region at stride minus, that I have some Euclidean path integral that prepares some state that then is evolved to the far future. In terms of a picture, it looks like this. So this, I have in mind the future half of the Penrose diagram here. And then at t=0 surface, that has 0 extrinsic curvature. This is derivative is 0 at that point. And I glue in a hemisphere. And I can do that smoothly. In other words, this is some complex time contour, where the Euclidean section prepares the state, which is then evolved forward in Lorentzian time. This right here, this is the t=0 surface. And in terms of that coordinate t right there, in fact, if I were to take, well, let me say what the contour is, it looks like this. So at this point right here is I pi by 2, and I go down, so I use a different color. Go down right there. If I evaluate that metric on that part of the contour, I just get a hemisphere. dt squared becomes minus dt squared becomes plus d tau squared, and the cos squared becomes the cosine squared. And then this, so that's this segment, the evolution right here. And then this Lorentzian segment is that part right there. And what I want to do now, I'm going to take the state seriously as an interesting state. I won't get into arguments about whether or not it's natural. The direction we're going to go with this is to try to compute the norm of this state once it's evolved to the far future. That's where we're going with this talk. So with this picture, I'm going to think of let me kind of interpret this amplitude, which I have in mind, like taking the gravitational path integral over geometries of this sort that are filled in by a Euclidean cap and where I fix boundary conditions in the far future. I can interpret this as a wave function in the following way, and then so I'm going to say that the cap here is preparing a particular state, the no boundary state. I'm going to denote that as like an empty set inside of the cap. It's getting evolved to the far future by Lorentzian time evolution to an operator I'll call V. U will be something else. And then when I fix data in the far future to have a well-defined path integral, what am I fixing in the far future in a de Sitter context? I'm fixing a conformal class of the metric at future infinity in the same way that in ADS-CFT we would fix the conformal class of the boundary metric. So for this geometry here, that metric is just the round metric on the sphere. So there's a metric G that I'm fixing, and I'm going to associate that metric with a rod. I'll call it G. This is all to say when I compute this amplitude, I have in mind a quantum mechanical interpretation that this is rho G, B, and then the no boundary state. And I can think of this whole thing right here, the no boundary state evolved to the far future. I'm going to call that the Hartle-Hawking state, HH. In which case, when I compute this amplitude, what am I doing? I'm looking at the wave function of the Hartle-Hawking state in the basis of states described by a conformal class of metric at future infinity. Sorry.
Hey, you answered most of the question I was going to ask.
Fantastic.
But
That's the best.
I'm still slightly so normally we would think of the Hartle-Hawking prescription as a prescription for wave function of the universe.
Yeah.
The version has like a 3 metric, or in this case a 2 metric as its argument.
Right.
And you're reducing this argument to just a conformal class.
Where does that come from?
Yeah, or how does it alter? We should be able to ask an analogous question, not at square plus, but somewhere
Sure.
at finite time,
Yes.
and clarify, are we summing over different metrics, all of the same conformal class, or?
Yeah, so what happens, so I'm gonna, indeed, we could work at some finite time. I'm going to work in where I go to the far future. And in that case, one way of thinking about why it's a conformal class is that so in the far future, again, let me borrow how this works in ADS-CFT. So in ADS-CFT,
Actually, let me say one more thing.
Oh, sure.
What you don't get to specify is the time, right? You get,
That's right.
Whereas you're somehow implicitly doing that by saying, I want to be
In the far future, where the spatial slice is asymptotically big.
I mean, one thing that you can do with the student I propose is you sort of you fix the metric except for a conformal factor, and you fix the extremely curvature trace.
Yes.
Is that effectively what you're doing here?
No. Although this is something that Dio has been thinking about lately.
I mean, that effectively lets you fix the time, because the extended curvature trace depends on the time.
That's right.
So I thought you were going to say that you fixed that to the asymptotic value.
No.
Well, how else are you ensuring that you're at the
Yeah, so what I really have in mind, my boundary conditions that I'm fixing are some asymptotically de Sitter boundary conditions. And those are labeled by conformal classes of a boundary metric because I can do a temporal diffeomorphism just like I can do a radial diffeomorphism in ADS that changes the conformal representative. I can enact a Weil transformation with a temporal diffeomorphism. So a simple way to see this, like if I, by my large...
What I would be worried about is that when you translate that back into the usual formalism, that means that your slice could be sitting at an infinite number of different times, all of which are asymptotic.
Yes, that's right.
Right, and presumably there's some infinity that you would get by not fixing enough terms in the argumentable function.
Well, maybe, let's see, the way that we, let's see. I think the way that this works in practice, here, maybe here's another way of saying it, is that by performing, okay, so if I were to consider computing this amplitude, but fixing my boundary conditions in the far future, I fix, and like what I really do is I fix the asymptotic region, I fix a cutoff slice at some very, very large time that I'll ultimately send to infinity. I fix them using defining functions the same way that I would in ADS, and induce an effective metric on that boundary slice. And I consider...
Because I think we can simplify the discussion a lot by just, for the purposes of this question, we can go to mini superspace. So in mini superspace, normally what you specify is just the radius of the spatial sphere, right? And that implicitly defines the time at which it sits in the settlement approximation. But all spheres are in the same conformal class.
Sure.
And so you would certainly have basically no information when you go over to the conformal class alone.
Right.
But you could, for example, restore it by instead specifying the trace of these extremely curvature or something like that. Otherwise, I think you're just summing over an infinite number of saddle points.
Well, maybe let me keep going. I think it'll be clear shortly that we're not summing over an infinite number of saddle points, that we're really counting it right. But let's come back to this. Let's come back to this point.
You might be fixing something else.
Yeah. So let's see. And this, okay, so we get a wave function out of this, which is a wave function that depends on this boundary metric. And what I'm saying is that one can, once you have this wave function in hand, you could, if you wanted to, compute interesting physics. You could compute equal time correlation functions on Scri plus using this, where this complex square would give you a probability distribution on the space of metrics. So for instance, if you were interested in O1, On, average at Scri plus, well, this would be some integral over metrics, and if we were considering not just pure gravity, but also some matter fields as well, that we would fix the matter behavior at far future. We would also have some integral over matter configurations. If we're just doing gravity, we would have an integral over metrics at future infinity, mod diff times Weil, psi HH squared, then our string of operators. And these would be cosmological correlations. In the Hartle-Hawking state. And, well, this particular state has the following feature that, I'll make the statement in d dimensions first. So in dS3, not just in dS3, at tree level, a semi-classical approximation, not computing loops yet, where I take this metric at future infinity to be now the round sphere plus some small fluctuation h, then the behavior of this wave function is e to the minus the sphere partition, or sphere action divided by 2, minus a term that's order h squared divided by g Newton. So this right here, why is this here, why is this here? This is the hemisphere action. So this is just what I get from the Euclidean cap. That makes sense. And then, well, I have some fluctuations. They're going to be controlled by something that goes like 1 over g Newton. This form looks like an integrated 2-point function of a stress tensor in a CFT. maybe it's not surprising for, this is similar to what would happen in ADS-CFT as well. And from this point of view, if you look at psi squared, so the probability distribution, here's, this is the order, at least at tree level, e to the minus sphere action. That is to say, it's parametrically the same size as the sphere partition function itself. Which is why you might think that these two things have something to do with each other. And the question that I want to address in this talk is whether or not the norm of this Hartle-Hawking state is related to the sphere quantum mechanically, in particular the one loop. And there's a reason why you might expect this to be true, which is the following. So we've said that this wave function comes from going up, or rather creating a cap, and then going up in time. So here's the boundary state. And if I consider the conjugate wave function, what am I doing? Well, I have a asymptotically de Sitter region, it's evolving forward, and then it's capped off here. Involved using the conjugate operation V. And when I'm considering, if I consider the norm of this Hartle-Hawking state, let's see.
Sorry, these V and V daggers are in reality just the identity, right?
Well, I'm leaving myself on why I said V dagger. I'm leaving it possible that it's not the identity. I don't want to. Like, in order to make that statement, I need to be able to say, for instance, that the no boundary state and the state that I prepare, that I characterize by conformal class symmetric at future infinity, live in the same Hilbert space.
Yeah.
For now, I'm not going to assume such a statement. I'm not going to assume that it's unitary, that it's one, or etc. But if it is a unitary operation, which is a lot like what you're saying, then what you would get
Yeah, it's identity.
yeah, more than unitary, that's identity. I mean, if you make the weaker statement that and what you're saying is you expect the evolution operator to be h equals 0. But if I just assume a weaker statement that it's unitary, then that operation, that's Hartle-Hawking state, and then I have, what I've really done when I compute the norm at infinity is I've inserted a projection operator effectively onto states at future infinity described by a single universe, in this case a sphere. And, well, if I think of that as no boundary V dagger, and then this projection V, I don't need these lines in between, I'm just changing on the fly what I had in my notes a little bit, then this projection should be morally like a resolution of the identity. V and V dagger would cancel against each other, and I would be left with just the norm of no boundary state with itself, which would be the sphere. And the reason why I am cautious, and I don't want to make this assumption that V is just the identity from the get-go, we already learned that this is some alternating phase. Because this right here, this should be non-negative. This is the contribution to a norm squared. So something is happening. And
Well, the conjugation seems to just be in the last line.
Perhaps.
Okay.
I just want to be agnostic about this. I mean, I can compute all these things as gravitational path integrals, and we'll see at the end of the day how the dust settles.
But I mean, you must have some alternative definition of the Hilbert space that you're building, right? The Hilbert space you're building is the Hartle-Hawking Hilbert space, then it's just trivially the case that these identical. Right? So
Well,
you must have some other meaning in mind when you write phi and HA.
If we were doing quantum field theory in a fixed background,
Oh,
I agree.
yeah.
I agree.
I'm not understanding why you're introducing this state on the throat, because that's sort of against the spirit of the whole thing, right? You're supposed to specify the state, you're specifying the argument of the wave function. And then
Yes.
you're just looking for ways of
That's right.
closing that off with no boundary. And in fact, if you introduce a perturbed state, like not something that's not a three-sphere, or excuse me, a two-sphere at the
Right.
top there, then you know the dominant configuration will not be around sphere at the throat either. So you know you've got to let the path interval do its work.
Right.
This is where that's being introduced.
Well, certainly my initial condition, that I need an initial condition to make sense of the path integral. And
Well,
then
that's
I need
not
an in-state. I'm just calling that in-state, the cap, I'm just calling it.
No, but you seem to be, the question is whether you're fixing anything about the shape of this cap.
No, I'm not. I want to, so,
In that case, what's the motivation for putting this cut there in the first place? I mean, you're just looking for a complex contour
yeah.
that ends up on the argument of the wave function.
Yeah, so I maybe one way of answering your question is I have to say so this is some particular geometry, some particular closed time contour. I have to say what do I do for fluctuations around it, especially if I make sense of the path integral. And what the conditions that I'll impose in that context are, it's stuck, are going to be regularity near here, and then I preserve my G out here at future infinity. Those will be the boundary conditions that I impose on fluctuations. Right, so.
Sorry, but then this V is the phase, right? I mean, at least on the saddle point. It's not the model. You're gonna pick up a phase. It depends on the length of time.
Why?
No, actually, well, okay, it depends on, so when I'm computing this amplitude,
Yeah.
I am going to holographically renormalize the de Sitter action, and that amounts to stripping off some very, very fast oscillating phase in front of that it would appear in the wave function that I would extract from solution to Wheeler DeWitt. And phase drops out of expectation values, and that phase indeed would be sensitive to the length of this time contour.
Sorry, but the phase that just appears in the overlap between G and HH, the fact that we interpret it as V having a phase, is something that we maybe imagine.
Well,
As in,
Yeah, you can interpret it as V has a phase that gets canceled out, or I could.
or you could just say that the overlap itself just has an overall phase.
That's right.
Time dependent. Dependent on the overall time which you put that.
That's right. So what I want to do though, okay, in computing this overlap, I mean, if you're happy with thinking it should be the sphere partition function up to factors of I and such, then okay, fine, you can consider this a precision check using the path integral that this is indeed the case. I think there's, I would be a little bit more cautious, at least that's my personal disposition, about asserting from the get-go that V is identity. I feel like that's something that we should check using the path integral rather than assert, and if it works out that way, fantastic, but if it's not, then it's good that we were careful. Maybe, let's see, yeah, I'm just in the interest of time while I keep going. So, the thing why is it the case that I'm doing three-dimensional gravity in this talk? Well, there's really two things that are simplified by going to three dimensions. The first is that the first simplifying features The first is that when we talked about, say, the Hilbert space of states at future infinity, if future infinity is a single sphere, I'm talking about conformal classes of the metric on a sphere, and there's only one such thing. So in other words, the Hilbert space of states corresponding to a single two-sphere is one-dimensional. And that will simplify things quite a bit. It means that when I talk about the wave function, this is just a number. It's a complex conjugate number. And then to make sense of the contribution to the norm squared, all I need is to have a notion of the norm of this state with itself. And then I'm done. So that's one simplifying feature. And the other won't appear so much in the talk, which is just that the functional determinants, I'm going to evaluate these amplitudes in one loop, and that involves some functional determinants, and those are much simpler in 3 dimension than in 4 dimensions.
So I didn't quite understand statement 1,
Yeah.
proof of statement 1. Are you gonna go?
So again, so states, I'm saying are labeled by conformal classes, the metric and future infinity. If future infinity, if I demand that it's a single sphere and not like a collection of spheres or a torus or something like this. In other words, if I project onto final states that are described by a single sphere, then that subspace of states is one-dimensional because there's a unique metric on the sphere, mod diff times file. Yes?
Is this specific about 3D or is it just
This is specific about 3D.
So at S3 there are multiple components?
Yes, yeah, there's infinitely many. In other words, if I wanted to compute this norm squared in 4 dimensions, I have a residual gravitational path integral at future infinity to perform over conformal over fluctuations around the round sphere mod diff times file. Here, I just have numbers.
Sorry, like a follow-up question, if you were in 4 dimension, like is the additional integral over component cost you do, like is it a finite dimensional or infinite dimensional?
It's infinite dimensional. Right, so maybe let's keep going. So this first object, GHH, this is the wave function. Maybe this gets at your question earlier about what, Raphael, about whether or not like I'm dividing or summing over too much. If I consider 2 different conformal classes for the boundary metric, 2 different conformal representatives, then it turns out this is not equal to psi HH G in this setting. There's an extra multiplicative factor. And a simple function I'll call e to the minus SP of omega G. What is SP? SP is a Polyakov action in this setting. So in other words, this wave function of the universe behaves like a CFT partition function in 2 dimensions. That's what you get from gravity. And well, CFT partition function of some central charge C has an anomalous dependence on Biology scalings. It's completely summarized by an object called Polyakov action.
So here G is a completely fixed 2-dimensional spatial metric.
Yes. This is, and again, this is at future infinity.
Well, wait, what makes what does that mean? Is it future infinity?
Well, one way of thinking about
It's a
it.
qualified metric, it's not a future infinity.
In a mini superspace like language, I guess the analog would be if my scale factor is very, very large, and then I look at the solutions to Wheeler DeWitt in 2+1, and then there's and if I change the scale factor by a bit, there's an extra anomalous dependence of the wave function on the change in the scale factor.
Yeah, it's usually a phase.
It's usually a phase, but here what ends up happening this particular thing, and so there's an extra phase in front that I've subtracted off using holographic normalization. There's an extra thing that's not quite a phase that's left over. This thing is characterized by an effective central charge, C, that has an imaginary part. That does lead to a phase, but there's a real offset when you go ahead and compute it.
That was sort of the non-trivial conformally scalings, right?
Yeah.
That are not just like a overall.
That's right, yeah, and that's a one loop effect.
Yeah.
So,
Sorry, so when you wrote down that expression over there on the right,
Yeah.
for correlators of O, what do you actually mean by the quotient by vial?
so what I really mean, what do I really mean by vial? Well, I really mean a division by vial.
But that only makes sense if psi HH is invariant under vial transfer.
That makes sense if psi HH has central charge 26. So this is what I'm getting to. So psi behaves like a CFT partition function, it turns out, if I include one loop effects of some non-trivial central charge. And if I look at psi squared, this behaves like a CFT partition function of a total effective central charge that's C plus its complex conjugate, which thanks to this one loop effect is exactly 26. It's just what I need so that I can make sense of coupling to world sheet conformal gravity if I think of future infinity as a world sheet. Yes?
Just, I mean, how this, like, there was a paper earlier about from the complex little
Yes.
stuff where they talked
Yes.
about how dS3, is this the same thing, like is the central?
So they're central, so yeah. So they're, right, so this, good. So there's two connections between what one superficial and one genuine connection between what they do and what I'm describing. So they have a world sheet model where I take Louisville at complex central charge, 13 plus I large, and I couple it to another Louisville at 13 minus I large, so that my total theory, or their total theory on the world sheet has C equals 26, and they couple consistently to world sheet gravity. So that part is superficially similar. The part that is a similarity in more detail is that for unknown reasons, there are correlation functions in their model that behave like CFT partition functions, acceptable wave functions, that they argue are really wave functions of certain states in three-dimensional gravity, maybe with particles of this same central charge.
So you would not, at this point, you would not say that the like cosmological correlation functions that are calculated are the same as these ones that you're talking about?
Pretty well, yeah. There's a question of right. So that their formalism is well adapted. Actually, there is some. Well, let's see. So I'm talking so far in this talk about something that's more lowbrow than what they were interested in, namely the case where future infinity is a sphere. They're unable to discuss that. What they consider are things like contributions to the no boundary wave, Hartle-Hawking wave function, would say future infinity is a genus 2 surface or higher,
If they,
and it caps off in the interior.
sorry, maybe if this is in the direction to ask that, but like in a situation where you took their model and you had a 3D sphere on either end and have three boundaries so you can do everything, would
Yeah.
it still be different?
Yeah, it's still different. Well, I mean, it's related in the sense that they're producing wave functions from which one can consistently use as inputs to define cosmological correlations, albeit in, you can think of it as a different kind of post-selection where you demand that future infinity, instead of being a sphere, is some other surface and maybe with some extra particles in there. But physically, they're the same sort of objects, but just with different final states. Yeah.
So I should have asked this much earlier, but I guess maybe connected to this question. why are you restricting, maybe you're not, but
Yeah.
you seem to be restricting to an S2 topology for the arguments of the wave function.
That's so far, yes.
And,
Why is this?
yeah.
The reason why I'm doing that is that those like there are many, like starting from the cap and going out to the future, there are many possible contributions to the wave function. There's like a genus 2 contribution, there's a de Sitter analog to Hartle-Hawking that fills in a torus at future infinity that's even simpler, and so on and so forth. All of these things have an on-shell action that's order 1. Well, I mean, 1 by GUT, but the imaginary part is 0. And as a result, if I think parametrically how big the wave functions are that I get from this, these sides are order 1.
So
Whereas-
you're just neglecting them because they're smaller.
Yeah. The sphere is the dominant contribution
Yeah,
to the
that's
wave
for
function.
sure.
Yeah. So that's why I'm focusing on the sphere.
But on the other hand, it seems like at the level where you're discussing the size of the Hilbert space, weren't you appealing to, I mean, isn't it important to restrict that? That seems more of
That's just a statement about, so what I'm implicitly doing, I'm saying states, the Hilbert space at future infinity is labeled by conformal classes of metrics on the boundary, and if my boundary is a sphere, that's one-dimensional. If it's a torus, then there's many, effectively that Hilbert space will be labeled by tau, complex structure, and for a higher genus surface by some more modular parameters. If my future infinity is a disconnected sum of things, then it might be even bigger still.
So this is really a truncated Hilbert
This
space.
is, yeah.
Good.
I'm considering I think maybe I said it too fast. For this part of the talk, I am considering something very simple, which is just the contribution to the Hartle-Hawking state where future infinity is a single sphere. There's many other contributions, and I want to compute the contribution just from that one sphere subspace. And that's what I mean by this pi1. This is like a projection operator onto configurations where future infinity is a single sphere. So let's see. So we have this magic happening so that these wave functions are acceptable to form essentially a quantum mechanical interpretation where I integrate over these metrics mod diff times phi at future infinity.
But sorry, just one question. In some sense, since the Hilbert space is one-dimensional, these wave functions just have a trivial inner product, right?
Well, I mean, they're still, if you will, I mean, what I really want to compute is this ratio. So, which graphically looks like I have the conjugate wave function, I have the wave function itself, and I want to divide by the inner product of the state at future infinity with itself. What is that? Well, we have some experience from computing similar inner products at asymptotia in JT gravity in previous work with Jordan. We claimed that we can do this by a short time path integral, where our two space-like surfaces are very, very close to each other near as you tend toward future infinity.
So shouldn't that be independent of what G is? Shouldn't that be, if the Hilbert space is one-dimensional, shouldn't that be equal to inner product of Hartle-Hawking with itself?
We would say that is a contribution to the norm of the Hartle-Hawking state. It's not going to be the whole thing. There's other contributions as well. I mean, like I can have two spheres at future infinity. I can have tori at
Can you
future
say
infinity.
again why you're computing this particular ratio?
If I want to compute the norm of this state at future infinity, not this particular part of it, but the full norm, you can think of that as inserting a resolution of the identity onto the Hilbert space of states at future infinity. And what I'm implicitly saying is that I can divide up that, I can resolve that identity into configurations where future infinity is a sphere, or two spheres, or a torus, or 6 tori of different complex structures and so on. Like there's many possible terms in this resolution, all possible configurations of future infinity. If I thought of future infinity as being some world sheet of an emergent string theory, then I'm summing over all, all world sheet topologies possible. And the leading the first contribution that I'll encounter that's very large is this one sphere contribution. And I'm calling that thing, in order to what is that one universe contribution? It's like operationally, it would be integral over metrics on the sphere divided by div times while of this psi HHG that gravity hands me. But I want to interpret this because physically there's just one such conformal class, and like this integral is really just summing over a single point. I'm interpreting this as for any choice of conformal representative G as the wave function at that fixed G divided by a normalization factor that would be coming from this measure of that one state with itself.
But if pi1 were the dominant contribution to that identity,
Yeah.
would it mean that HH, pi1, HH would be approximately equal to the norm of HH, so independent of G?
If that was the case, yes.
I see. So if you're going to find that it's that the inner product that you're computing on the right depends on G,
Yeah.
then that implies that pi1 is not the dominant contribution to the identity.
Yeah, what we'll see is that, well, time is running out very swiftly.
You can take a little bit.
Yeah. Well, I don't, okay, I'm not going to recess, I'm gonna act like I didn't hear it. But, I'm sure there's people in the room that are not, have things to do too, prior to sitting in the seminar. But, maybe, let me pivot a little bit here. So, what I claim is that we have a gravitational path integral for this normalization, and a gravitational path integral for the objects appearing in the numerator. The denominator is a short time path integral, and the sort of one-line heuristic explanation for why such a thing should compute an inner product is remember what happens in quantum field theory or in quantum mechanics. The short time limit of transition amplitudes becomes the inner product. That's the same idea here. And what we can do is we can independently compute all of these things to one loop. They're just some ratios of functional determinants. It's worth noting, so this numerator I said has an effective central charge of 26. So does this denominator, actually. Which means that this ratio that I just constructed is an honest to God number. Something that's well defined. And let's see, so in the interest of finishing in a timely fashion, let me say, I kind of set up what problem we're interested in. So what are the three kind of main results that we are establishing? Albeit with the resolution error because paper is not on archive yet. So statement one is that this one sphere contribution to the norm is at least a one loop order, is the magnitude of the 3-sphere partition function, rather than the 3-sphere partition function itself. So one way of thinking about why it's a modulus, well, I have a number, I have its complex conjugate, and this inner product here is positive. It's an inner product. And in fact, it's a positive using the usual integration contours of 3-dimensional de Sitter gravity. One way of thinking about why we don't run into the same kind of factors of I that appear in Euclidean gravity is that we're doing a Lorentzian path integral. So we don't have to rotate modes as one does in Euclidean gravity. That's one statement. The second statement is that if we consider this norm more generally in a semi-classical expansion, well, there's a contribution to this from one sphere, from two spheres, from three spheres, etc., as well as tori, higher genus, and the contribution from spheres alone, disconnected spheres, exponentiates. And the third result that we're finding, there's another object that we can consider that I haven't written on the board here, which is just the global amplitude itself. So I interpret that as a transition amplitude from state in the past to state in the future. There's just one possible state in the past, one possible state in the future. And if I normalize this using the short time path integral, the inner product, I can interpret this long time evolution. Let me call that thing U. What we're finding is that this U, if I restrict myself to these one sphere initial and final states, that this is just a projection operation itself. It's basically the identity operator on this subspace. So a way of interpreting that is that affected Hamiltonian here really is zero. That's how I would interpret this. And I guess, let me say, so it's 4:40 now. Maybe let me say a few words about what's involved in showing some of these statements. Obviously, I can't show these statements in the time remaining. Say 5 minutes, I'll try to wrap up by. So, try to comment a little bit on the first line. So, first line, we're interested in some ratio of functional determinants appearing in gravity path integral. If you've never seen this before, this kind of analysis before, it's relatively fun. There's a quadratic action for fluctuations around any solution to Einstein's equations with positive cosmological constant and Lorentzian signature that with an appropriate convenient choice of gauge fixing, an arc psi version of transverse gauge, looks like this. Where here, H bar mu nu is traceless. H is the trace of the metric fluctuation. And B and C are the Faddeev-Popov ghosts that are required to gauge this. And D squared is just box. And so what one needs, here already you see the conformal mode has the opposite sign as the traceless symmetric tensor. So in Euclidean signature, that leads to the usual conformal mode problem. In Lorentzian signature, no such rotation of the conformal mode is required. And what you would end up with, at least up to things like zero modes, when you compute the one-loop determinants around a given background, is a determinant in the numerator, again up to issues with zero modes, of minus I d squared acting on a vector plus 2, and then the denominator, determinant accepting zero modes, minus I d0 squared plus 4, so the d squared acting on a spin 0 operator, and I guess a plus I. Determinant minus I. Determinant acting on the spin 2 field minus 2. And at least in all these cases, all these backgrounds that we're dealing with, you have a maximally symmetric space or a little tiny cylinder thereof. And so you can completely enumerate the mode spectrum of the Laplacian in all these different sectors. And if I work, as a fun aside, if you work at fixed angular momentum on the spatial two-sphere, the spectral problem that you're dealing with is identical to a classic quantum mechanics problem, that of the Poschel-Teller potential. So you can borrow from lots of nice undergraduate quantum mechanics results to proceed. But you can compute these determinants in closed form. It's not, like I'm not a functional determinant guy, even I can do it. So, that's one comment. And I can, if you're interested in some of the details, how, for instance, you can see the modes on the sphere pop out from some of these determinants, I can tell you a little bit more afterward. As for the exponentiation, maybe the simplest way to observe this, suppose that we consider not the one sphere contribution to the norm, that means here, but the two sphere contribution. So I have nothing, some cap convert to two spheres in the final state. The leading contribution to this, the thing that has a semi-classical saddle, is where there's two Euclidean caps. And you get a product of two disconnected geometries. I picked different conformal representatives, G1 and G2, for metrics on the sphere. You would interpret that product as the wave function of the Hartle-Hawking state in the basis of two sphere final states. Now, of course, this thing is nothing more than the wave function in the single one squared.
Sorry, you're not claiming that the two-sphere states form a basis, right? You just mean the amplitude.
I just mean the amplitude.
Yeah.
But then, well, if I consider this the contribution of two sphere final states to the norm, if I consider psi squared and then divide, again, because there's actually a unique metric on these, and I can't tell the difference between which universe is which, there's a one-dimensional space of two sphere final states. And again, I can write down the contribution to the norm as the wave function squared divided by the inner product of the states with itself. But now, so this part is basically the square of the numerator is the square of the one universe probability. But the denominator, well, I'm looking at short time path integrals that fill in a little bit of time evolution near future infinity between two spheres and two spheres. And there's two ways of doing that. Do this, or I can do this. And that leads to a factor of 2 in the denominator, and you repeat this for n boundaries, and you get an n factorial. So if you will, the gravitational path integral is telling you that these final states behave like identical bosons. And, okay, so in an equation then, this becomes the 1/2 times the one universe convolution squared. The n component one proceeds in the same way, and you exponentiate. Now, my concluding comment for this talk is that what we're seeing from this is that norm of HH is this nice giant sphere part. as an aside, I think Sidney Coleman was arguing for something like this long ago in the 80s, maybe with a little bit of gesturing involved, but and before knowing that the sphere partition function had a phase in it. But here you do get that answer, or at least that's the contribution from spheres. And there's other topologies. And if I'm just interested in, say, the contribution from tori, higher genus behaves in a similar way. This contribution was recently computed by Victor Godet, building on prior work of Castro and Maloney. And this contribution diverges. And the way that it diverges is that, so I said earlier, the wave function, the amplitude for, or I have a torus at future infinity and it's filled in with some de Sitter version of a handle body, that the wave function is order 1. This contribution is really some integral d2 tau, some function of complex structure, and this function is order 1, but there are singular points. So the integral diverges. And where does the integral diverge? It diverges in those regions of moduli space where the torus is getting very, very long, or it's pinching off. And there's a similar statement for higher genus, where you get divergent contribution. This was computed by the CLS crew, the complex Liouville string crew. And where those divergences, again, there's some order 1 thing, you integrate it over moduli space of higher genus surfaces, and it diverges when the higher genus surface has some shrinking cycles, when it's developing a very thin handle. And the observation I want to make to conclude this is that this sort of behavior that one sees here is reminiscent of what happens in cold sheet string theory again, in the context of d-instanton perturbation theory. So there, what one has is that there are divergences that appear at any fixed order in the genus expansion, but then the sum of all those things is finite. And here, we see something similar, and maybe that shouldn't be so surprising, since the integral that we're computing in order to compute this norm squared is like an emergent world sheet theory at stride plus. However, there's, I say it's reminiscent. No one knows how to verify these words in any degree of rigor. So with that, thank you very much for your attention.
Like before, okay, so just based off what you said about how, this is sort of a trick about like computing the like short time.
Right.
Like the thing I would have done to compute GG with a picture I would have drawn to say compute GG would have just been the thing at the top. So why is this not one?
Well, let's see. So why is it not the one? I can be very operational with what I mean about this short time path integral and what I mean by the long time one in terms of spectrum of fluctuations. So let me, just for illustrative purposes, not do the problem with the whole metric fluctuation, but just consider something simpler, just a scalar, a fixed mass squared. Right, so I want to talk about the modes that obey boundary conditions on here and here. And if I work in a sector of definite angular momentum on the 2-sphere, and I rescale my fluctuation by a factor of cosh t, then the spectral problem, which here is d squared minus m squared, phi is lambda phi, it becomes this Paschal-Teller problem. So it becomes minus d squared dt squared minus L plus 1 over cosh squared t plus 1 minus m squared gamma squared. F is lambda f. And what happens in the global context is t runs from minus infinity to infinity. So if I subtract off the constant, I'm looking at this quantum mechanics problem of a 1/cos squared well. This is the effective minus t at infinity. But if I'm looking at and that problem has scattering states. It turns out this is, if you've ever taught this, then you know it's a reflectionless potential. So things come in and they don't scatter off, they just proceed through. Very special. But there's also bound states. There's, for L here, there's L bound states. Concentrated, of course, near the center. And there's some spectral density associated with the scattering states, and there's some, of course, the discrete spectrum. But in the short time path integral, we're sitting way out here. And in that case, we don't see the bound states anymore, but we do see our scattering states. So then this is a very non-trivial fact that if I consider the ratio of determinants relevant for 3D gravity, including the bound states and the scattering states and so on, and I effectively strip off the free particle, like regularized by the free particle version of the answer, that I get exactly identity.
I see.
That's the non-trivial statement there.
Maybe this is a silly question, but in the case where you have two spheres, like
Yes.
the inner product G1, G2, G1, G2, why do you consider just the contraction between the 1, 1, 2, 2, 1, 2, 1, 2, and not the bra, ket?
Yeah, so I'm obeying, okay, I'm obeying ordinary quantum mechanics here, right? So I'm saying my gravity path integral prepares an amplitude, I have an amplitude complex conjugate, and when I consider, I'm not changing the rules of quantum mechanics when it comes to defining inner products or that there's variations of inner products. I'm using the GPI to define an inner product that's just fixed. It doesn't have any fluctuations in it whatsoever.
Okay, so if you were to do that, and you were to compute, let's say, G1, G2 absolute value squared.
Yeah. And you would get.
Then you would get different.
Then you would get a different answer. That's right. So if I change the rules of quantum mechanics, then yes, I would get a different answer.
I wouldn't call it changing the rules of quantum mechanics. I would say changing which contributions the path integral receives, right?
Well, it's changing. I mean, if I say that an inner product has a statistical distribution rather than being fixed, that's what I mean by changing the rules.
Sure.
So I mean, maybe the difference, like why this shouldn't concern you, is that in contrast with what happens in JT, here my inner product, like these are, I'm not claiming at all that there's a dual description of any of the things that I'm describing in this talk. Maybe there is, in which there's inner products and there's some statistical distribution of those things. Here I'm just talking about the bulk, well, including asymptotia, but the quantum gravity, quantum mechanics, Hilbert space of states and inner products.
I guess at that point, though, where you are saying that the path integral can connect to different the different spheres, that is not quite this what we do when we do a typical path integral. You are kind of setting up the rules.
Well, let's see. So,
Such that you allow the connection between.
But you shouldn't think of this as a square or an overlap.
I understand.
Just a state with two boundaries in the past, two boundaries in the future, you just sum over all possible boundaries connecting the two.
I understand. I could also say the same about summing over all possible geometries connecting the boundaries.
it's more like what happens in many particle quantum mechanics.
Right.
If identical particles.
Yeah. I guess like the statement would be like the right way to write the G1, G2 state is as like how you would write this state for two identical bosons. And
Yeah.
the intersection there is not the G1. Oh, yeah.
that's or at least that's how I'm defining things. As an aside, yeah, nowhere here have I presume said any words of like dS3 or hope that there's a holographic dual or any other such thing. Maybe one point that I would at least be happy with, if there was something of a dual description, the natural expectation is that it would live at scry and that it would produce these wave functions. But in order to extract physics, we need the inner product, we need the resolution of the identity of future things, so we can talk about correlations. And is there a dual description of that object or not, is an interesting question.
I mean, normally, so you set the cosmological constant in 1,
Yes.
but if you hadn't, it would still be 26, right?
Yes, that's right.
Whereas a dS3 it would not. Like the central charge that idea talks about is not.
Yeah. If it was dS3, you would say that this thing is, this is the 1 by G part. Claim this. That 13 offset is a robust result from bulk quantum gravity. I should have mentioned too, this 13, I just asserted it like it was obvious, so this was a non-trivial one-loop computation that I did with Jordan and Alex Maloney some years ago.
Any other questions? Kristan again?